Natter that's going to come up and talk about high induction diffusers. So Andrew is with the Master Group. He's been there for a couple of years now. And he's now, correct me if I'm wrong, you're the ventilation product manager there. He's given out this presentation on high induction diffuser, which is a new trend going on in the city. We're seeing more and more of these products being sold, being installed in numerous buildings. So beyond further ado, I'd like to ask Andrew to come up, present the speech.
Hi everyone. So welcome to today's presentation on high induction diffusers. It's a real pleasure for me to be here. This is the second time I present this topic at the ASHRAE. First time I presented the topic, it was at the Moncton chapter. So it went very well. The presentation lasts approximately 1 hour. Tops 1 hour, yeah, don't worry. We'll be done by 9. And my name is Andrew. Yeah, I'm the product manager, like he mentioned. Basically what that means is that I'm the link at Master Group between the engineering team of our manufacturers and the sales team at Master Group. So whenever there's very technical questions, I get to answer them, and also I do presentation on anything that's new products line that we sign. The high induction diffusers, it's not a new technology, it's been out there for a long time, but it's been there's been a hype around it in the recent years. The last 5 years, we've seen more and more high induction diffusers being sold. So that's why I chose this topic today. So the outline of the presentation, we're going to talk about, so we're not going to talk only about high induction diffusers as a product. It's really oriented on comfort, energy savings, ASHRAE standards. And at the end of the presentation, we're going to do an air outlet selection. That's the only part where it's going to be product oriented. Because if I spoke about a diffuser for a full 1 hour, eventually I start losing part of the crowd. So it's really going to be on ASHRAE standards and comfort and everything. So if I'm going to talk about high induction diffusers, the best place to start is to explain what induction is and what differentiates a high induction diffuser from a standard diffuser. So what is high induction? So if we look at isothermal airflow, this is isothermal airflow. The reason it's isothermal is it's straight. If it was a heating, you would see it move a bit up, and cooling, move a bit down. And if you look at the black arrows right there, this is room air that's being induced by your primary air. So the primary air is the air that's coming out of your diffuser, and the secondary air is all the induction, it's all the room air that's being induced by your primary air. So it's kind of an entrainment ratio. And the higher your induction ratio, the more you get room air mixing. So the advantage of that is that you have a lower temperature gradient across the room. So there's two advantages to that, is that you're more comfortable because everybody in the room feels the same temperature. So if I'm standing here and somebody's standing at the other end of the room, we're going to feel the same temperature. But also it's not going to be any temperature gradient vertically. So you're not going to have cold feet, and I mean that literally. So the formula is the induction ratio is your total volumetric flow, so induced plus primary, divided by your discharge from outlet, your primary air. So if I tell you a standard diffuser, like any cone diffuser, like these diffusers right here, they have an induction ratio of 4. That means for each CFM delivered through the diffuser, there's 4 CFMs of room air that's being induced by your primary air. A high induction diffuser has an induction ratio of 17. So you have much more induction, and that's going to allow us to have better comfort and ultimately energy savings. So the reason I'm presenting high induction, yeah, there's the hype, but the hype is there for a reason. We're investing much more money nowadays in high efficiency HVAC systems. Comfort is becoming something that's very important. You want your occupants to be comfortable. If you're designing for an office building, for example, you want your employees to be comfortable, because if your employee is comfortable, he's going to perform better at work. And you're going to reduce the absenteeism from your employees. So it's a question of comfort, but it's also a question of energy saving. So we're seeing much and more air handlers, for example, that are variable volume. So variable volume systems are great for energy savings, but they pose a challenge for the selection of your air diffuser. For example, if you're modulating your airflow from 400 down to 100 CFM per diffuser, are you going to select your diffuser for maximum airflow, or are you going to select your diffuser for minimum airflow? Typically, we're going to select them for maximum airflow, because if you would do it the other way around and you would select it at minimum, well, once you reach maximum, you're going to have a lot of noise issues, static pressure losses, too much throws. So we select it for maximum airflow, and we kind of hope for the best once it reaches minimum airflow. But the real answer is you need to select a diffuser for maximum and minimum airflow. The reason being is that once you reach minimum, if you don't have enough CFM coming out of your diffuser, the airflow is just going to start dropping down vertically. It's called a cold air shower. And it's going to start dropping vertically on the people sitting under the diffuser. So for example, anybody that's sitting under a diffuser and we're modulating down the airflow, you're going to get high velocities of cold air showering on your body. So if you're supplying air at 55 degrees Fahrenheit, and that air doesn't have enough time to mix with the room air, you're going to get a shower of cold air at high velocities, and it's going to reach your body at somewhere around 60, 62 degrees Fahrenheit, and that's very uncomfortable. So that's one of the reasons we promote high induction diffusers on the comfort side. And we invest just as much money in high efficiency controls, we insulate our piping, we insulate our ductwork, all in the purpose of energy savings. But if we don't properly select our air outlets, then the whole system can be viewed as a failure. And when I say failure, it's not that the system is not going to function properly. I mean it more in the sense that you're going to see things like that. Every time I go on a job site, I like taking pictures of kind of ventilation fails, we can call them. And this is one of them there. This is at the Uber offices. You know those illegal taxis? They have a headquarters. And look at the diffusers here that they have in their office building. Half of the diffuser, and each of them, if you look at them, they were taped off. And the reason these diffusers have been taped off is because, like I said, we have a variable air volume system. So whenever the air modulates down, for the people who work on the weekend shift, there's less people than on the weekday shift. So the heat load is lower, and the airflow modulates lower. So everybody that's sitting under one of these diffusers right there, they're getting cold air showers on their body. And we got a call where they asked us, come take a look at our ventilation system and propose a product for us. And that's exactly what we did there. We proposed a high induction diffuser. The first thing to notice is that they're using those standard cone diffusers. And they're good diffusers. I'm not bashing the cone diffuser. It is a very good diffuser. But the cone diffuser needs a ceiling because of a Coanda effect. You need to have a ceiling so that the air, once it's leaving the diffuser, it sticks to the ceiling. You need the air to stick to the ceiling so that when it reaches the occupied zone, the velocity is going to be lower and the temperature is going to be closer to your set point temperature. So there's two mistakes here. You're using a cone diffuser for variable air volume and you don't have a ceiling. So this one is actually my favorite. So this here happened in two steps. The first step, and I think everybody's seen that quite often, is the plexiglass that's chained under the diffuser.
Yeah.
We often see that because whenever you get that cold air shower, well, the plexiglass gives you a second horizontal push, so that the air, once it reaches the occupied zone, is closer to your set point temperature. But even that wasn't enough there, so they just completely blocked the diffuser with, it was paper towels, brown paper towels. So they completely just blocked the diffuser. So the occupants are comfortable now. But what they don't realize is that they created another problem elsewhere in the system. If you're blocking that diffuser, that air needs to go somewhere. So So if that air is coming out from another diffuser, that other diffuser has longer throws, higher static pressure, longer throws, higher noise values than anticipated. So you're solving your problem, but you're creating another one elsewhere in the system. So when you design your ventilation system, where I'm going at with this is that you want to have the most perfect design, the closer to perfect as possible. Because whenever end users start tampering with the systems, it's really dangerous for the whole system. They don't have a view of the whole system, the end users. They only see what's happening in their zone. This is another example. The picture on the left, they were a bit more creative in blocking the grill. This is a sidewall grill. And they blocked it with a binder. I don't know how.
Whatever works.
Exactly, whatever works. So all I'm trying to say here is that you want to try to avoid tampering with your ventilation system by the end user. So if we're going to talk about comfort, I explain what induction is. Let's define what comfort is together so we all start on the same basis of comfort, and then we'll see how we can solve and quantify comfort. And comfort is a subjective thing. I know this for a fact. I've been living with my fiance for the past 2 weeks, and we already have a battle for the thermostat. You know, I'm comfortable at temperatures around 65 degrees Fahrenheit. She, on the other hand, she's comfortable at temperatures of around 75 degrees Fahrenheit. So we always have to do a compromise and put the thermostat at 75 degrees Fahrenheit.
That is compromise.
Exactly. I learned this pretty quickly.
Good.
But in a one-sentence definition, comfort is you're thermally comfortable when your body's heat loss equals your body's heat production without noticing any changes to your internal thermal regulating system. So what that means is that since your body's temperature is hotter than its environment, you're constantly dissipating heat to the environment, and you want to do so at a comfortable rate. So if you're dissipating too much heat to the environment, you might start shivering. Or if you're not dissipating enough heat to the environment, you might start sweating. So those are noticeable changes to your internal thermal regulating system, and you don't want these things to happen. You want to dissipate heat at a comfortable rate. And there's 4 ways to dissipate heat. One of the 4, and that's one of the most important ones, is radiation. So basically you're transmitting electromagnetic heat waves to the environment. And the formula, if you remember your heat transmission class, it's epsilon, that's your skin's emissivity. You have a sigma, which is the Boltzmann constant. And then you have temperature A times 4 minus temperature B times 4. So basically it's just to tell you whenever you have a temperature gradient between your skin's temperature and any other surface, radiation goes extremely fast because the temperatures are times 4. Conduction, so this one's kind of negligible unless you have a super cold ground, but typically you don't, so this one's a bit negligible. So conduction is when there's a direct contact between any surface of your skin and any other surface. Convection basically is the moving air that sweeps off the radiated heat and transfers it to the environment. And that's directly proportional to your air velocities. And last but not least is evaporation. So like I was saying, if you're not able to dissipate enough heat to the environment, you're going to start sweating. And you don't want this to happen. If you're in an office application, you see people sweating, automatically that's a sign that they're uncomfortable. So everything I just described is how your body can transfer heat to the environment, or the mechanisms to transfer heat to the environment. And the comfort parameters are what control how much heat you transfer to the environment. So there are occupant factors and space factors. The occupant factors, the first one is your metabolic rate. You have to ask yourself the question once you're designing a system, what are you designing your systems for? Is it a gym where your metabolic rate is of like 7 mets? Or are you designing a office application where you're at approximately 1.1 to 1.3 mets? The other one is the clothing rate, so it's the insulation level of your body. So the clothing rate basically is defined in the unit clo, CLO. And the way I'm dressed right now, with a shirt, jacket, pants, socks, everything, that's around 1 CLO, the clothing rate. If you're wearing, for example, in summertime shorts and a short sleeve polo, that's around 0.5 CLO clothing rate. The space factors, I'm going to present them in this graph here. So this is a typical space here. You see your comfort height, as defined by ASHRAE, is always at 6 feet high. So whenever the air reaches that zone, you want to make sure that the velocities are always under 50 feet per minute. Anything higher than that, you could feel the draft. So the space factors are the velocities of the air. You want to control your temperatures between typically 73 to 77 degrees Fahrenheit. You want to have a maximum relative humidity of 60%, minimum 30%. The minimum humidity is not defined by ASHRAE, but anything lower than 30 is just too dry, so try to always stay between 30 and 60. So maximum velocity of 50 feet, I said that. You want to avoid hot air stratification at all time. First of all, it's a waste of energy. You have all that hot air that's just sticking to the ceiling. And second of all, you want to have a maximum temperature gradient vertically of 5 degrees Fahrenheit if you're standing. And if you're sitting down, that's 3.6 degrees Fahrenheit. So those are a lot of factors to keep track of as an HVAC designer. And ASHRAE, they invented something called the effective draft temperature to help us keep track of all these factors in one single formula. So the effective draft temperature depends on 3 variables. You have Tx and Vx. So those are local temperature and velocity measurements anywhere across the room. And Tc is your set point temperature or your ambient temperature. And with the effective draft temperature, what it is basically, it's kind of the wind chill factor when you're watching the Weather Network. You know when they say it's minus 10, but it feels like minus 20? This is exactly what the effective draft temperature is. It tells you the effect of air velocity on your body. And if you notice this side of the formula here, Vx is subtracted to 30. So any velocity, in fact, over 30 feet per minute contributes to the feeling of coolness. Because if, for example, your set point Tc is at, let's say, 72, and Tx in cooling mode, you measure it at 71. So 71 minus 72, that's minus 1. Any velocity over 30 is going to reduce your effective draft temperature. So it's just to say that any velocity over 30 is going to contribute to the effect of coolness, and that's true in cooling and in heating mode. If you do it the other way around, if your set point is 72 and you measure 73, well, the effective draft temperature is going to always go down with velocities higher than 30 feet per minute. So I mentioned you want to have a maximum velocity of 50. That's good, but if you want to go even better, 30 is the maximum velocity. So the effective draft temperature brings me to the next slide. It's ADPI. It's the Air Diffuser Performance Index. This is how you rate the effectiveness of your ventilation system. The higher your ADPI, the more efficient the ventilation system that you have. So basically what ADPI is a bunch of effective draft temperature readings evenly distributed across the room. So let's say all those red dots there are where I measured my effective draft temperature. And to have a pass, you want to have an effective draft temperature of between -3 and +2. If you're outside these bounds, it's a fail. So let's say all the blue dots are passes and the red ones are fails. Out of the 12, I have 10 that are passes. So 10 on 12, that's 83% ADPI. So that's a pass. Anything over 80% ADPI is good for your design. The only challenge with ADPI is that if you're actually taking temperature and velocity measurements across the room, that means your system is already installed. ideally you want to know at the design phase what's going to be the efficiency of your ventilation system. So there is one way to go around that. It's actually, ADPI has been linked to something called the T50 on L. It's the characteristic length of your diffuser. So at the design phase, you're able to know based on the heat load, your room dimensions, the throw, the type of diffuser you have, what's going to be your ADPI. But that's kind of it's a guess measurement when you do it that way. The best way to do it is ideally either do a mock-up or do a simulation, VFD, not VFD, CFD simulation. Ideally, that's what you want, and there's going to be a difference between whatever you calculated based on the characteristic length and the CFD analysis. So it's the as-built ADPI is never going to be the same as whatever you predicted. That's one of the challenges with ADPI. And the second challenge is that it's only valid in cooling mode. So that's great for areas like California where you're cooling all the time. But here in Canada, we're approximately heating half the time, cooling half the time. So in reality, half the time, we have no idea what's going to be the efficiency of our HVAC system. So in Europe, instead of ADPI, what they use is induction ratio. And that's not recognized by ASHRAE. But, well, that type of induction ratio with temperatures is not recognized by ASHRAE. But it is a good way to determine the efficiency of your HVAC, of your ventilation, both in cooling and heating. Because all it is basically is a bunch of temperature readings across the room. So there is delta TXY and delta TO. And basically delta TXY is T room minus TXY. TXY is the temperature of the air once it reaches the occupied zone here. And delta TO is T room minus TO, which is the supply air temperature. Everything's in Celsius in there. That's because induction is a European technology, so they work in Celsius over there. And if you notice, anything that's a standard diffuser, whenever I say standard, I actually mean the cone diffuser, because it's the most common diffuser out there. So it's 0.25 in induction ratio. If you do 1 divided by that, it's actually a temperature ratio. So if you do 1 divided by your temperature ratio, you get your induction ratio of 4 for a standard diffuser, and 1 divided by 0.06 will give you 17 for high induction diffusers. So I spoke a lot about the cone diffusers compared to the high induction diffusers. Let's see head to head what it looks like when you compare both diffusers. So I took an application where it's easy to calculate. What I mean by that is that the X plus Y distance is 8 feet and the throw is 8 feet. So it's kind of easy to calculate. If you have a throw of 8 feet and your X plus Y distance is 8 feet, and your throws at 50 feet per minute, that means the velocity once it reaches the occupied zone is 50 feet per minute. It kind of just made it easy to calculate like that. So your airflow per diffuser is 220. Your distance, X plus Y, that's X and that's Y. All right, that's what X plus Y distance is. Your supply is 55, your room temperature is 72, so that gives you a temperature difference of 17. And the first thing we want to find is what's the velocity of the air once it reaches the occupied zone. And the values in blue are all the catalog values. So the cone diffuser is manufacturer B, and high induction is manufacturer A. And I took all their throw, nose values, and static pressure losses from their respective catalogs. So the noise values, if you notice, first thing, the throw of the high induction is much shorter than that of the cone diffuser. The second thing you might notice is that the noise values is 26 decibels here, while the cone diffuser is at NC12, which is close to 22 dBAs. And the third thing is the static pressure loss. With the high induction, you're at 0.1 inches, while the cone diffuser is at 0.04 inches of static pressure. So far, I mean, if you look at it, the cone has higher throws, longer throws, it's more silent, and lower static pressure loss. So it seems like a better deal, and it's cheaper, it's more inexpensive. But it's basically, what's the trade-off for comfort? If you look at the induction, the temperature ratio, like I said, it's 0.25 here and it's 0.06. So yeah, you have more throw, higher noise, more static pressure loss, but you're mixing your room air so much better that at the end of the run, you're actually saving money on the electricity bill because you're not overheating or overcooling certain spots. So the mixing ratio, it's 1 divided by the temperature ratio, so we have 17 and 4. So if we have 50 feet per minute velocity of air once it reaches the occupied zone, like I said, the calculation is that it's 8 feet to x plus y, plus the throw is 8 feet at 50 feet per minute. So we reach the occupied zone at 50 feet per minute. The other one has a throw that's actually much shorter. So we reach the occupied zone at 30 feet per minute. So I was mentioning that 30 feet, it's kind of, if you're able to get that, it's a much more comfortable situation to have. And if we go with the formula of induction, we're able to find the TXY temperature. TXY temperature is the temperature right here, once it reaches the occupied zone. This is actually the most critical area right here. This is the most critical area of the room. Because when two air streams collide, it's as if it hit a wall and they're going to start dropping down together at high velocities. So if you're able to have a good effective draft temperature here, then you're going to have a good effective draft temperature everywhere else across the room, because that's the most sensitive spot where two airstreams collide. So for example here, between the two diffusers over there, this is a very sensitive spot, and everywhere else is the same. So the temperature here is 71. I found it with this formula. This one here is 67.8. So first of all, you're reaching the occupied zone at temperatures much colder with the cone diffuser than with the high induction. And the second thing is, if you do the effective draft temperature calculations, your effective draft temperature here is going to be -1, because you reach at 71, minus 72, and there's no velocities because you actually reach the zone at 30 feet per minute, while this one here is at -5.6, the effective draft temperature. So that's a fail for the cone diffuser. It might not be everywhere across the room fail, but at this particular spot, the most critical spot of them all, the cone diffuser would fail. While the high induction has a pass, and a very good one, because anywhere between -3 and +2 is a pass, and he's right there in the middle. So it's a very good pass, in fact. So what's the trade-off for comfort? Are you willing to sacrifice a bit of static pressure, a little bit more noise, but for higher comfort and ultimately energy savings? Now, it might not sound so good for the high induction, more noise, more static pressure, but I have to explain from where these values come from. So, the cone diffuser, I took its values from manufacturer B, which is a North American manufacturer. There's a lot of them that produce the cone diffuser, and all North American manufacturers test their diffusers the same way. And it's based on ASHRAE standard 70, which basically allows you to test the diffuser in lab conditions, where you have 8 times the equivalent straight duct, like the equivalent diameter. So if you have an 8-inch neck, you could have 64 inches of straight duct before your diffuser. That's for an 8-inch neck. If you had a 10-inch, that would be 80 inches of straight duct before reaching the diffuser. Have you ever seen a job site with 64 inches inside the ceiling area? Nope. Somebody ever seen it? Raise their hands.
It was an accident.
So whenever you open any catalog of any North American manufacturer and you look at the sound values, the throw values, the static pressure losses, these values are based on these lab conditions. While the other one, the high induction, it's actually a European diffuser. So they test them, they don't test them with these same lab conditions. They don't believe in ASHRAE there, they have something else. So whenever they tell you it's 34 decibels, it's actually 34 decibels in the field. And the second thing is that they come with a plenum typically. I saw one in the entrance there. And if you see, they all have a plenum. If you go to Europe, every diffuser has a plenum. And it's not that the Europeans are better than us, it's just that over there the cost of electricity is so much more expensive than it is here, that they're going to save every kilowatt hour that they can. So that's why they use a plenum for every diffuser. It's not just a standard plenum. Ideally, you want to have a stabilizing grill so that the pressure inside the plenum is equal everywhere across the plenum. So instead of shooting straight into your diffuser, you shoot into the plenum, you pressurize it, and there the air comes out evenly across the face of the diffuser. So if you don't have a plenum, you're going to use a flexible connection and connect it straight to the inlet of your diffuser. So instead of being vertically, you're going to come horizontally, probably, depending on the contractor, swirl around the diffuser a little bit because it doesn't want to cut the flexible duct, and then connect into the neck of your diffuser. So what that does is that you have a kinked inlet connection, somewhere similar to that here. It's not going to be straight, it's going to be more kinked. And all of that is coming from the engineering guides of any North American manufacturer. I'm not inventing this, I didn't even draw this, I took it straight from one catalog. So what they say is, if you have a kinked inlet connection, that adds 12 to 15 decibels to your manufacturer's rating. So if we were at 22 decibels, we just added 12 or 15 to that. So we're at 22 plus 12, that's 34 to 37 decibels. Just because you're not using a plenum, or you don't have 64 inches of straight duct before your diffuser. The air distribution pattern can be greatly affected. So what that means is that whenever you read a throw, and it says, for example, 8 feet, well, that's based that it's going to be symmetric on both sides. So you get 8 feet one side and 8 feet of throw the other side. But if you're using a flexible connection, you're coming horizontally, and the air doesn't have the time to stabilize before reaching the diffuser, you might get 80% of the air going one way and 20% of the air going the other way. So whatever throw calculations you did at the design phase are not really working anymore in the field, just because of the flexible duct connection. So if we look at, go back to this drawing here, imagine here we calculated maximum 50 feet per minute, and this one is throwing 80% of the air that way, this one is throwing 80% of the air that way. You're going to have high velocities in this zone. And the third one is 90-degree bend and flex adds 0.07 to 0.1 inches of static pressure at 700 feet per minute inlet velocity. So let's see what all that does. Exactly the same table that I showed you previously. Let's see what all these things do to the values we have. So like I said, the throws don't change, but the noise values, we're at 26. It stays at 26 because of the plenum. While this one can go up to 34 decibels, unless you're using a plenum with the cone diffuser. If you are, you won't have any problem. The plenum is not exclusive to high induction. Any diffuser, if you use a plenum, you know that you're going to have whatever rating the manufacturer gave you at the design phase. And your static pressure losses, if you add 0.07 there, you're at 0.11. And your velocities, like I mentioned, they're going to be much higher if you're in that zone where you're getting 80% of the air. So in reality, there is no trade-off to high induction. In reality, you have less noise, less static pressure loss, more comfort, and energy savings. So let's continue talking about comfort. This is ASHRAE Standard 55. The latest edition of it is the 2013 version. So that's the last edition of the ASHRAE 55 standard. And this is the standard that discusses comfort. Anything related to velocities, temperatures, anything related to comfort is inside that standard. And like I said 30 feet per minute earlier. Let's see what ASHRAE 55 mentions in terms of velocities. So the way ASHRAE rated comfort is through statistical analysis. Basically, they took a group of people, they put them in a room, and they started subjecting them to different temperatures, humidity ratios, different velocities, different clothing, different activity levels. And every time they were subjected to a certain condition, they would ask the people to vote from -3 to +3. Basically, if you're at -3, you're too cold, -2, you're cold, all the way up to +3 where you're just too hot. Anything that's +2, +3, or -2, -3 is considered a fail for ASHRAE. So you have to be between -1 and +1 for your fail. And the way they calculated things statistically is that if you want to have a maximum PPD, this one here, predicted percentage of dissatisfied people, if you want to have a maximum of 10% dissatisfied people,
Use that one last night in the election. There were a lot of PPDs last night.
so you want to be between -5 and +5 if your PPD is under 10%. That's the way they calculated it statistically. So on the next slide here, like I said, the PPD has to be maximum 10. And this is a PPD versus air velocity graph that you can find in the ASHRAE 55 standard. And if you look at it here, and you take a temperature of approximately 22.5 degrees Celsius, that's around 72.5 degrees Fahrenheit, which is a common design temperature, I believe. You want to have a maximum velocity of 27.6 feet per minute, as defined by ASHRAE. So we can round that up to 30. This other graph here, this is a graph for your average speed versus your operative temperature. The operative temperature is kind of it's complicated. ASHRAE does that sometimes, complicates things. But basically your operative temperature is kind of a mean, it's an average temperature between your radiant temperature and your air temperature. And there's 3 zones. There's the dark gray, the light gray, and then there's the yellow zone right there at the bottom. So if your occupants have control over the airspeed, so if for every 6 occupants you have 1 control for airspeed, there's no maximum velocity. But like if we look at this example here, nobody has control over the airspeed. Nobody has a small fan next to him or anything like that. So you fall onto the light gray area where occupants control is not required. And in that light gray area, depending on your clothing rate, the 1.0 is on the left with the dotted lines, and then the 0.5 clothing rate for typical shorts and t-shirt attire, it's on the right. And if you look at here, if your temperature is higher than 22.5, 72.5 degrees Fahrenheit, you need to follow this line to know your maximum velocity, and it could be up to 160 feet per minute. But if you're under 22.5, which is most applications and office applications were under 22.5 degrees Celsius, you need to be at a maximum of 30 feet per minute. That's 0.15 meters per second, which is the equivalent of 30 feet per minute. So ASHRAE goes as high as saying you need to have a maximum 30 feet per minute if your temperature inside the room is at 72.5 degrees Fahrenheit or less. So this one here is a flow chart. You find it in ASHRAE 55, page 11. Basically, it sums up everything I just said, but more in a flow chart kind of a graph. So you start here, it asks you, what's your metabolic rate? Are you above 1.3? If the answer is yes, then you're not designing office application. You're probably designing something like a gym, and you don't have a maximum airspeed limit. If you go to the gym and you're running on the treadmill and you're hot, getting a draft of cold air actually feels good. It doesn't bother you much. The most sensitive applications are office type of applications where your metabolic rate is very low. So if your metabolic rate is lower than 1.3, the second question is, do occupants have control over the airspeed? If the answer is yes, then you have a maximum of 240. But I've never seen an application where people could control the speed of their HVAC system. So you fall into the no category, and if your temperature is under 72.5, maximum velocity of 30 feet per minute. So that's pretty much it for comfort. I skipped the noise control part. Basically, that was mostly related to the plenum, where I was showing that putting a plenum, you don't have to add the 12 to 15 decibels to the manufacturer's rating. Now, for energy savings, basically the biggest loss that you get out of your ventilation is through hot air stratification. Whenever your hot air stratifies, you get higher temperature inside your ceiling area, and because of that, you have higher losses through your building's envelope. So you want to, all that heat that's just stagnant up there, you want to find a way to throw it back into the occupied zone. And let's say you're heating through the diffuser, and you're returning your air from the return. I think that's what we're doing here, right? I don't see any baseboards. Oh yeah, we have a few baseboards. But let's say the type of applications where we don't have baseboards. Let's say the engineers, we want baseboards. Sometimes the architects, are there any architects here? No. But mostly the architects, they would tell you, I want to remove all the baseboards for architectural reasons. So when you do that, it poses a challenge for ventilation, because you're going to diffuse your hot air from the diffuser in the ceiling, you're going to return from the ceiling, and hot air has this tendency to just, it has a lower density, so it just stays high. It doesn't naturally come down into the occupied zone like cool air does. So it poses a challenge for ventilation if you want to supply hot air and return through the ceiling. So to avoid that, you need to have a diffuser who's going to give enough velocity, enough vertical push for all that hot air to reach the occupied zone. Like I mentioned, the high induction, that's more high induction motion. It has a swirling motion, the high induction. If you compare it to a cone, the air comes out horizontally like that, while the high induction would come out swirling. And that swirling motion, combined with hot velocities, allows your air to reach down into the occupied zone. So typically, you'll be able to reduce the air inside your ceiling space from 28 down to 23. So all that hot air is recuperated and sent down into the occupied zone. I know there's people that might be skeptical, and I have to mention it's not only about the diffuser, it has to do a lot about your control sequence also. So the thing is, when we heat through the diffusers in Canada, the type of control sequence we use is similar to that. So the y-axis is basically your CFMs, your airflow, and the x-axis is the temperatures of the room. So all the purple area is your heating loop. And if you're going to heat through a diffuser, let's say like the cone diffuser, so the air typically comes out at lower velocities than high induction. And if you add to that the fact that you're operating and heating at minimum airflow set point, and that's the typical control sequence that we see in Canada, then first of all, you don't have a lot of CFMs. You're operating at minimum CFM, you're distributing hot air through a diffuser that has low velocities. Your hot air is just going to stagnate there. It's just going to stay in the ceiling. It's never going to come down into the occupied zone. And whenever I do an airflow test at our lab, we have a lab in Montreal where we could do smoke shows. Any diffuser that we have, we could test them at different CFMs, at different temperatures, and we can inject smoke into the airstream to show exactly the type of airflow that we have based on the diffuser. And the test that I enjoy doing is always the cone diffuser in heating mode. And you see the smoke just staying on the ceiling, never coming down into the occupied zone. That's heated air that we're just wasting. And what happens often is that some of that air is just bypassed to the return. So you heat that air and then you return it. That's a big waste of energy. The best type of control sequence we can use in Canada is something similar to here, where in heating mode, you want to be as close as possible to your maximum airflow. And in return, you reduce your delta T. So you have a bit cooler air at higher CFMs, higher velocities. So your chances of that air reaching the occupied zone are much greater than throwing hot air into a diffuser at low velocities. So if we could adopt one type of control sequence, the one I recommend is this one there. And I did one project like that in Montreal, and we were at 80%, at heating mode, we were at 80% of the maximum CFM. And some might wonder, well, if you're throwing more air, that means your fan in your air handling unit is working more. Yes, it is, that's added cost, but it's greatly offsetted by the energy savings you'll have by going with this control sequence. So because of that, like I mentioned, you have some of your hot air that's bypassed into your return. What happens is that in ASHRAE Standard 62, whenever we do our fresh air calculations, ASHRAE says here, line number 3, if you're supplying air through the ceiling at least 8 degrees Celsius above space temperatures and ceiling return, your efficiency, your EZ, your zone air distribution effectiveness factor, is 0.8. So that means if you calculate a certain amount of fresh air, let's say 1,000 CFMs, if you calculate 1,000 CFMs of fresh air, you need to divide that by 0.8. So that means you're at 1,250 CFMs of fresh air. That's an added 250 CFMs of fresh air that you need to heat or cool, humidify, dehumidify. So you need to treat all that fresh air, and there's a cost related to that. So if you can reduce the amount of fresh air, that's energy savings. If you look down at the bottom, there's a small note, and it's a bit bigger here. It mentions, as an alternative to using the above values, EZ may be regarded as equal to air change effectiveness determined in accordance with ASHRAE Standard 129 for all air distribution configurations except unidirectional flow. So let's see what ASHRAE 129 has to say. ASHRAE 129. If the ventilation air within a space is perfectly mixed, then the outdoor airflow rate to the ventilated space would be identical to the required rate of outdoor airflow. While perfect mixing is an idealized airflow pattern, it is the objective of high induction air diffusers commonly used in mechanically ventilated commercial buildings. If these diffusers are performing properly, then a measurement of E using this standard will yield a value essentially equal to 1. So what ASHRAE is saying basically is, if you're able to reach that perfect mixing, then your efficiency is going to be of 1, and you could reduce the amount of fresh air that you're supplying to your building. If it's minus 30 degrees outside, you're going to be glad that you're reducing the amount of fresh air. So I took a typical building, forget Montreal, should have said Ottawa. So typical building in Ottawa, area of 45,000 square feet, 200 people working there full time. So the calculation is 5 CFM per person multiplied by 300 people, that's the amount of fresh air, plus 0.06 CFM per square foot multiplied by 45,000 square foot. It gives you a total of 4,200 CFMs of fresh air. It's estimated that for each CFM of fresh air, it costs like $6 to treat that air. It's 2.8 for heating and cooling costs, and 2.4 for humidification, and 0.8 for dehumidification. I got these numbers by asking a few contractors, what's the rule of thumb for each CFM for cooling, for treating fresh air? And I did an average from all these answers, and it was estimated at $6 per CFM. So if we were at 4,200 CFMs calculated, then with high induction, with a 1.0 effectiveness factor, you stay at 4,200 CFM. At 0.8 factor, you have to be at 5,250 CFM of fresh air. So that's an annual cost of $31,500 to treat that fresh air, compared to 25,200 CFMs. And the savings would be 20% for a total of $6,300 per year. That's on a year-round basis, by the way. It's $6 per CFM on a year-round basis. So going with high induction, a higher efficiency factor allows you to reduce fresh air and then save on your electricity bills. And those are dollars for the province of Quebec. I think it's a bit more expensive here in Ontario. So you're actually saving a bit more money than that. So that's pretty much it for energy savings. We talked about comfort. The last is air outlet selection. Basically, I think the question that's burning on everyone's mouth is, what's the cost of these? They're great, they save energy, they're more comfortable, but it's probably more expensive. So let's find out. I took a typical room. The first room here is an open type of room, a bit like here in this restaurant, where there's 4 diffusers if we're using a typical cone diffuser. And the second room is 2 office buildings that are separated. So office 1, office 2, each one have 195 CFMs. And the open area has 140 CFMs per diffuser times 4 diffusers. Now those are the costs when the same contractors that I asked how much does it cost to treat fresh air, I asked them how much does it cost to install diffusers. And this is the answers that I got. For each secondary branch, it's about $65. That includes your hardware, so there's a damper, there's your duct, and then there's your flexible duct. Each diffuser for a cone diffuser is the most inexpensive diffuser out there, and they're approximately at $32 per diffuser. Your labor for installing the diffusers is $85, and then you have balancing costs. You need to balance every diffuser to make sure you're at the correct CFM. So that's $30 per diffuser for a total of $212 per diffuser. Multiplied by 6 diffusers, you're at $1,272 total for the job. The advantage with high induction, because I was mentioning you can use a plenum, so you don't have the added sound values, the added static pressure loss, and it doesn't affect your airflow pattern. So you're able to throw more air into a diffuser without having any negative effect. So we're at 280 CFMs per diffuser, and there's only 2 of them in the open area. Now for the offices, there's not much we can do. It's 1 diffuser per office, so you can't cut a diffuser in half. So it's 1 diffuser per office still here. The same cost as before, except for the diffuser, which is estimated at $144, including the plenum. So it's a bit more expensive for the diffuser, but it's a total of $324, but instead of multiplying by 6, you're multiplying by 4, because there's less diffusers. So the total is $1,296. And if we compare both of them, it's $1,272 versus $1,296. So it's approximately the same cost for high induction versus a standard cone diffuser at the end of the run, including installation, hardware, balancing cost. But you have the added benefit of more comfort and more energy savings. So yeah, so that's pretty much it for the presentation. I think it was much less than an hour. So just want to recap. Basically, what defines comfort? It's ASHRAE standard 55, and to rate the efficiency of your HVAC system, it's through ADPI, and you want to have ADPI always over 80%. That depends on your air velocity, your temperatures, and you want to avoid at all costs cold air dumping. If your ADPI is equal to 1, I didn't mention that one, but ADPI equal to 1 is actually the equivalent of saying it's perfect mixing. This is something that's accepted in the industry. If your ADPI is 1, you can consider that you have a perfect mixing scenario. And like I showed in the first slides where I took the most critical spot and we still had a pass at the effective draft temperature. So if you pass there, you pass everywhere and your ADPI is 1 automatically. So that means you have perfect mixing. You have less hot air stratification and you can reduce the amount of fresh air that you're bringing into your building. And ideally, you always want to put a plenum on your diffuser. Whatever type of diffuser you're using, whether you're going with the cone, the high induction, linear diffuser, use a plenum because it's going to allow you to always keep the mentioned performances by the manufacturer. And you'll get a uniform airflow pattern. That's pretty much it. Yes?
About 10 slides ago,
That wouldn't stop.
you were talking about the noise,
Yeah.
relative noise.
Okay.
I thought you skipped over that too quickly. I made a note that one of them had 26 dB, the other one had up to 34 dB.
Yeah.
That's a huge difference. Because every 3 dB, you're doubling the noise. So 26 to 34, you're 2 times 2, that's 8 times the noise. That's pretty severe.
But 34 dBs is still pretty low in terms of hearable sound, right?
You can go up to 34, and it's even more. I added 12, but it's 12 to 15 decibels in reality. So it's 34 to 37 decibels. I took this from ASHRAE. Honestly. This is how ASHRAE mentions it. It's, if you have a thin connection, you have 12 to 15 decibels. Up to 12 to 15, because they consider kind of a worst case scenario installation where the contractor probably looped a few times around the diffuser. You know.
He's right though, saying that 3 dB is doubling
Yeah,
the noise.
3 dB
But
is
you have to
doubling.
bear in mind that the original noise is very low. So you double a very low noise level, it doesn't, in actual working space, it doesn't mean a lot to us because we don't really notice that it's becoming noisy. If you double really low, then okay, then it's still really low. And so 34, as Lam Cheese just said, 34 is still fairly low. Anyway, so what you're saying is that the turbulence caused by the flexible duct causes the increase in in noise. Yeah, makes sense. True.
Any other questions?
Are you talking about a specific brand?
Well, there's a few brands.
Yeah.
Can I name them? No.
No?
There's a bunch of brands. Mostly they come from Europe. Yes.
On that demonstration of the layout, we went from 6 diffusers with the standard cones down to 4.
Yeah.
How were you able to go from 4 to 2 in the open area? Is that because of the better distribution or better airflow diffusion?
Basically, is that the way we mostly design our HVAC, our ventilation systems, is we try to limit the amount of CFMs per diffuser. I rarely see more than 200 CFMs per diffuser, mostly because with cone diffusers, you're connecting your flexible duct straight into the inlet. So what that does is that it adds sound, it adds static pressure, it affects your throw pattern. So to kind of compensate for that, what we do is that we reduce the amount of CFM per diffuser to kind of minimize all that turbulence effect.
And you still have effective distribution.
Exactly, yeah. So if you have a plenum, you're able to eliminate all those field realities, the fact that you have flexible connection, added sound, added all that. So because of that, you're able to throw more air per diffuser. You can go up to 400 CFMs per diffuser. I limited my example to 280.
Right. Okay.
But with high induction, I've seen a lot of applications where they go up to 400 CFMs per diffuser. So if, let's say, each of one of these diffusers, they're at 200 CFMs, then we could reduce by 2 the amount of diffusers total. So they're more expensive to buy, but you get less diffusers to install, less diffusers to balance, less secondary branches, hardware.
Right, but you're still assured that you have adequate distribution to the perimeter areas of the area.
Oh yeah, definitely. Yeah. In fact, you want to have as much air per diffuser as possible, because that's what's going to create the highest amount of induction. The more air, the more velocity, and the more induction.
So you're talking about the roof diffusers. So the same type of diffusers are also used for the floor diffusing systems. So what's the trend right now for using the diffusers from the floor instead of from the roof?
I know that these high inductions, yeah, they have a model for floor diffusers, but I haven't seen many applications for floor diffusers.
So it's still very limited in the market.
Yeah. You know, the floor diffusers, the problem is that if you have a diffuser here and then you put a table over it, or you put a plant over it, or...
So the layout is one issue.
Yeah. So I think that's one of the reasons I don't see a lot of these floor diffusers a lot. The same goes for these, the domes that you install on the wall, the low velocity air displacement diffusers. They exist. A lot of manufacturers have them, but we don't use them in Canada because with low velocities, you can't heat because your air is going to go straight up to the ceiling. It's only valid for cooling mode. So this is another type of diffuser that exists that we just don't use here in Canada.
All right, thank you a lot. Thanks a lot, Andrew.
Thank you.